Hello, this is video number 6 from C6 Chemistry Out There. My name is Mr. Clee and this is about ozone and CFCs. So the aim of this video is that after you've watched it, you should be able to describe what ozone is and how it forms. You should also be able to give the properties of CFC and explain how CFCs can deplete the ozone layer. You should also be able to give some alternatives to chlorofluorocarbons. So here it is. This is ozone, which is O3. Ozone is a pale blue gas. It's very damaging. It's a major pollutant at ground levels. However, it's really important in the upper atmosphere. Ultraviolet light provides the energy source that causes oxygen to react to form ozone in the upper atmosphere. It's a multi-stage process, but basically all you need to know is that 3 O2 molecules form 2 ozone molecules in the upper atmosphere. Ozone is really important in the upper atmosphere. It's really important because it absorbs ultraviolet light, and ultraviolet light is a really damaging part of radiation. It's an ionizing radiation that causes damage to people. It causes increased risk of sunburn and skin cancer. It also causes cataracts. This is a cataract here, and it also causes aging in the skin. It causes wrinkles and things like that as well. But the major two things that it does cause that are really damaging are skin cancer and cataracts. So moving on to CFCs. CFCs are chlorofluorocarbons. They're called this because they're basically made of chlorine, fluorine and carbon. There are many different types and they are damaging to the ozone layer, and the reason that they're damaging will become clear shortly. This is trichlorofluoromethane. The reason it's called trichlorofluoromethane is because it's got 3 chlorines, trichloro, 1 fluorine, fluoromethane, because it's essentially the structure of a methane molecule. It used to be used in refrigerators. CFCs were used because, one of the main reasons they were used is because they were so inert. They didn't react with anything. For that reason you could spray it by your face in an aerosol and it wasn't really a problem. The problem was at high altitude, ultraviolet light in the stratosphere broke down the CFCs. It broke down in such a way that it formed something called a chlorine-free radical. This is a chlorine-free radical. It basically means that it's a chlorine atom with an extra electron. It's really damaging. These chlorine-free radicals break down ozone in a number of steps. The first one is that the chlorine-free radical reacts with ozone to form oxygen and another free radical there. This free radical then goes on to react with another ozone molecule. This process leads to the production of another chlorine-free radical. Because of that, what we have is essentially a chain reaction of ozone breakdown by these chlorine-free radicals. The overall process is the reverse of the formation of ozone. So it's 2O3 gives you 3O2. This major breakdown, these chlorine-free radicals break down ozone so quickly that it's led to a major depletion of the region of the atmosphere that contains ozone, and it's letting much more ultraviolet light reach the surface of the Earth and reach people. Right, there are other properties other than how chemically inert they are that made CFCs useful. They were the low boiling points, so they were always gases usually, and they're also insoluble in water. So the first key date is 1973. In 1973, concentration of CFCs started to be measured in the atmosphere, and it was found, because they were so chemically inert, that the amount of CFCs, or in particular trichlorofluoromethane, was almost exactly the same as the amount that had ever been made. So all the CFC was accumulating in the atmosphere. This happened at roughly the same sort of time that scientists realised that CFCs acted on ozone to break it down, and that a single chlorine, just one chlorine radical, could break down 100,000 ozone molecules, and we were making 1 million tonnes of CFCs every single year, of which all of that pretty much, was ending up in the atmosphere. Once you coupled all that information with the fact that the unusual conditions over the poles meant that ozone levels vary there naturally anyway, you ended up with a situation where there was a huge depletion of ozone over Antarctica. Far more than anyone ever expected. This region here is a hole in the ozone layer. It's not a hole in the atmosphere, it's just an area where the stratosphere, the layer of ozone, is not present anymore. And that was basically been created. It's larger than the entirety of Antarctica by the production and the accumulation of these chlorofluorocarbons. So because of this major link between the level of chlorofluorocarbons and the depletion of the ozone layer, it became increasingly clear that something needed to be done. So in 1987, an agreement was signed in Montreal, Canada, called the Montreal Protocol. It basically bans pretty much every single CFC, and a result of this, the ozone layer has started to recover. But because of how chemically inert CFCs are, and because of how damaging they are to ozone, it's going to be a very long time before the recovery is complete. Alternatives include molecules like this. This is a hydrofluorocarbon. They've got very similar properties, but we've got one major distinction, and there is no chlorine within this molecule. Because there is no chlorine within this molecule, it means chlorine radicals cannot form, and therefore it is not damaging to ozone in the same way that CFCs are. So, in summary, ultraviolet light causes the formation of ozone from oxygen at high altitude. The CFCs are insoluble gases which were used in refrigerators and aerosols before they were banned. Ultraviolet light causes CFCs to break down into chlorine free radicals, which lead to a chain reaction and breakdown of ozone into oxygen. And because they have been banned in the Montreal Protocol in 1987, they have been replaced by hydrofluorocarbons, HFCs, which have similar properties but do not contain any chlorine, so make no radicals. Thank you very much for watching.